This is lecture number 20 about the thermal properties of material. In fact, we started the topic and I finished the portion on change of melting temperature for nanoparticles. Now, as you know, thermal properties has two components. One is the melting temperature, that is reduction of melting temperature because of the nano size. And the second one is the thermal transport, how the heat gets transported during different kinds of operations. And the effect of size on that is the topic of discussion today. Well, in the last lecture, so as I said, we started this new topic on thermal properties of nanomaterials and discussed about the melting temperature of nanomaterials. And I showed you by different thermodynamic models how the melting temperature of nanomaterial will be varying depending on the size of the nanomaterials. Today, first we will do some recap of this thing and then we'll go on to the new topic. So as you know, every lecture I ask this question to you. If you have any questions regarding this topic, please keep it in your mind, and whenever we'll discuss about these lectures, you can always ask these questions. So as the beginning of the lecture, let me reiterate, thermal property of nanomaterials will have two components. One, the melting temperature of nanomaterials, other one, the thermal transport. And the first one, which is the melting temperature of nanomaterials, has been already covered. So what we did in that? Well, what we did in that is very simple. Basically, first we need to know about thermodynamics of melting. Okay, what is that? Well, thermodynamics is basically talks about free energy versus temperature plots, and as you know, below the melting temperature, solid phase is stable. Above the melting temperature, liquid phase is more stable, or stable actually. So because of these aspects, free energy curves will have a crossover at the melting temperature, and we can actually calculate the heat of fusion, or the latent heat of fusion rather, by using free energy concepts. That's what I did in the last lecture, and we have discussed many of these things very categorically, how this can be obtained. Okay, you can see here it is given. Well, most important thing for this discussion is how the melting starts. Normally, for a free nanoparticle, melting will always start at the surface. Okay, that's very clear. At the surface, melting will start. So hence, the liquid which will nucleate at the surface will slowly grow and move inside the solid spherical nanoparticles. Well, you can use any kind of shape, but for the sake of simplicity and make the things clear, we use the spherical nanoparticles and showed how the liquid front, which is forming at the surface of the nanoparticle, can move inside and it can melt completely. And this is how the melting normally happens in nanomaterials. It's very rare that liquid will nucleate inside the nanoparticles, somewhere middle or anywhere actually, here or there. It's very, very unlikely, because to nucleate liquid you need to have certain kind of surface, and that surface is provided by the outside surface of this material. Upon knowing that, what we did is simple free energy calculations. Free energy of melting for the bulk, that's given by L multiplied by delta T by Tm into volume of the liquid, and then surface energy balances. Surface energy of the the surface energy of the liquid plus surface energy of solid plus liquid minus the surface energy of solid at the beginning. And then by doing the calculation, we could show that when the thickness goes to very small, then we can arrive in the relationship between the change of melting temperature, that is of the nanoparticle, that is Tm minus T actually. T nano is equal to Tm multiplied by 1 minus 2 gamma SL by L0 into R. Well, that's not the always case. Some of the cases, nanoparticles may not be free. They will be sitting on a substrate, or they will be embedded in a matrix. In that cases, we need to use the concept of Young-Ripley equation to calculate the angle of weighting. Okay, and depending on that angle of weighting, basically that angle of weighting will be depending on the the balance of the surface energies or the interfacial energies between solid liquid, solid matrix, liquid matrix, and you know this relationship cos theta is equal to gamma Lm minus gamma Sm by gamma Sl, and then we can actually justify under what conditions temperature will go above the melting temperature or temperature will be below the melting temperature, or otherwise you can have superheating or you can have depression of melting temperature. Okay. So, that is about the recap. Now, let us discuss about the thermal properties of the material. So, thermal properties of the materials are very important, you have to understand. They are very, very important. Why? Because many of the many of these semiconductor devices or microprocessors, like in a computer or in a mobile phone or even in a normal machine where electronic devices are used. Okay. The goal is basically to transfer the heat away. Remember, many of these components which are used in a computer or in a laser or in any other device will be in nanometric scale. That is, the thin films which are depositing on these material on these components will be having thickness less than 100 nanometers. So, because of these aspects, they are nanosized. So, therefore, the heat generation in these materials will be quite large, because they are doing operations. When you are operating a computer or operating a mobile phone, you are doing all kinds of operation. Every operation needs generate heat, and this heat needs to be dissipated. Otherwise, temperature of the component will increase very rapidly and it will no longer function. So, therefore, the goal of these kind of thing is to dissipate it or transport the heat away as quickly as possible. But there will be other applications like thermal barriers. Okay. There are many such applications like in turbine blades, or even other cases of thermal barriers are required, where you need to be reduce the thermal conduction. So, heat transport, how is heat transport happens in a material? You have any idea? Well, heat transport can happen in two ways. Normally, we know heat transport happens by electronic conduction, right? Electrons are the best conductors of heat and electricity, right? And they can transport these things simply by going to high energy level. As you provide heat energy to a system, electrons will be energized, they will go to the high energy level and they can dissipate the heat. But that is only possible in cases where large number of electrons are available, like in a metallic materials where free electrons are easily available. But for what about semiconductors or insulators or maybe some non-metallic materials where large pool of electrons are not freely available, their heat transport must be happening in a different way, right? So, their heat transport happens by what is known as a lattice vibration or phonons. Okay. So, in metals, electron mechanism of heat transport is significantly efficient, and phonon processes, then the phonon processes due to the fact that in metals there is a large number of free electrons are available and electrons are not easily scattered. Okay. Electrons can easily move and take out the heat, they are not scattered. That is the advantage of metal, but in case of non-metals that is not the case. Electrons will not be easily available, and even if they are available, they will be scattered because of many scatterers available in non-metals. Okay. Obviously, scatterers will always be available in metals, but they will be relatively less in numbers. So, in those cases, it is only the lattice vibrations of the phonons that dictates the heat transport, right. So, before we go into discuss about the effect of the electronic conduction and the lattice vibrations conduction conduction to lattice vibration, let us first discuss about these aspects in a quite different way. So, I know that all of you know something about electronic conductions, okay? The energy levels, band diagrams, you are a little bit aware of that. Okay. So, when we will bring it back when at the end of this lecture when we talk about quantum confinement of electronics levels. So, basically what does it mean to say is that before we go into effect of these nano size on the conduction of heat by electron or the phonons, let us first discuss about what these are. That is very important. As you know, heat conduction is governed by Fourier's law, right? All of you know that. So, if you have a small piece of sample, length is L, okay, and cross-sectional area is A, and you have a hot end to cold end, heat will be transported from hot end to cold end. The Q is the heat, amount of heat transported per unit area per unit time perpendicular to the plane of the surface of this material, that is what is known as a flux. That will be equal to thermal conductivity multiplied by what? Thermal conductivity multiplied by Ka. A is this cross-sectional area and the temperature gradient, that we know. That means Q is proportional to basically del T by del X in one dimensional case. That is what is shown here. This is the case. This is the proportional to del T by del X. So, if that is the case, so what is the important aspect here which controls the heat transport and which is the intrinsic property of the material is the thermal conductivity, right. So, thermal conductivity K of any material will have two components, thermal conductivity to electronic conduction and thermal conductivity due to lattice vibration, correct. So, now design of materials in this aspect is basically to look into these two separately, but we know that they may be they will be related to each other, but basically most of us or the scientists in the world, they always like to have the electronic contributions and the lattice contributions separately and see in which material whether electronic conductions or the lattice vibration related conductions, which one is higher, which one has significant role. So, this is basically the things. Now, if you know the length scale or applicability of these things, if you consider an aircraft or a human, okay, you can understand that they are pretty big, right. Even a computer is also pretty big, but if you look at a microprocessor model or a blood cell or maybe MOSFET, okay, or if you look at even nanotubes, nanowires, they are pretty small. So, therefore, Fourier's law obviously will be applicable to all, but the transport in case of nanoscale material like in case of MOSFET, NEMS, nanotubes or even microprocessor models will be governed by particle transports. Okay. That means, it will be governed by either electrons or the phonons. Okay. So far so good. So, let us talk about what are these aspects, because that is something which is you should know very well. This is a one dimensional or two dimensional lattice rather. As you see in periodic lattice, you have atoms at each cross section, each points actually here, everywhere, and these are basically arranged in a nice periodic manner. So, there is a periodic potential exists in this material because the atoms will have positive protons and the neutrons, and they are surrounded by electrons. Okay. And now, as I said, in metals, electrons are freely available because electrons are not bound to any particular atom. They are most likely behave like electron cloud, right. So, because electrons are freely available in metal, if the moment you heat up or provide the heat to the system, electrons will take out the heat, they will get energized, and that is how they can conduct the heat or they can transfer the heat actually. That is the important thing. You can also have holes like in semiconductors, which can also act as a transporting agent for the heat, right. That is possible. But other thing which is possible is that as you heat the material, now listen to carefully me, as you heat the materials, what would happen? As you heat the materials, the atoms will also vibrate from the equilibrium positions. As the atom vibrate from the equilibrium positions, they can actually get pushed or pulled. As they get pushed and pulled, they create a vibration in the material or vibration in the lattice, okay, correct. So, if this atom, particularly say these atoms or this set of atoms are moving like this, or this set of atoms are moving like this, they are going to make a push when they come close, or they are going to pull each other when they are going away. By doing that, that means they will be acting like a simple harmonic oscillator, and by doing that, a wave will be created inside the material that can propagate, and that wave can then carry the heat, and that is what is known as a phonon or lattice vibrations. Okay, am I clear? So, let me tell you again. So, as you heat a materials, the atoms sitting at each of these lattice positions, they will also vibrate, right, from the mean or equilibrium positions. As they vibrate, the atoms can push or pull each other. As you see, if they are coming close to each, they will push, and they are going away from each other, they will pull, right. So, whatever the situation is, whether they are pushing or pulling, it is lead to creation of a vibration in the material, right? And because of this vibration in the material, the wave will be generated inside the material, and that wave is known as a lattice wave. Okay, fine. So that's the basically things which is known as a phonon. Now, this can help in two ways in the material. One, the heat transport; other one is the sound, movement of sound inside the material. That's something which is very well known in the system. Or let me just tell you in a very clearly manner what is a phonon is. Okay, now the question is, people always ask how heat spreads in the material. Obviously, one is electronic, other one is the lattice vibrations. They are nothing but a low frequency vibrations, okay, for the sound, and high frequency vibration for the heat. Okay, so phonons can be considered as a particle of heat actually in a material. So in a crystals, as I showed, atoms are nicely arranged in a uniform repeating way. When heated, the atoms will oscillate in the crystal, behaving like a spring, right? Just like a spring. I will come back to it very soon. Atoms are oscillating, and they will behave like a spring. So if this atom is moving like this or this, the springs will get pulled and pushed, right? You know that, right? So any kind of crystalline structures, the bonding can be thought of like springs actually. We know that. I am not going back to it, all of you have learned about it. So they are actually like springs by which this bonding has happened. So as you move the atoms from its mean equilibrium position because of the application of heat, the spring will be pulled or pushed. And because of this, okay, when the push and pulling happen, it can set up a traveling wave to the crystal. And so that is like a sitting on one edge of a humpling. You can also set up vibration along the length of the surface, right? That's exactly same as like that. So you can see when you are playing a piano, okay, as you see, if you press the keys, okay, you can see on the other side where the piano is open, how the wave moves. It is exactly like that. So by hitting, you are pushing these atoms, or you are basically pressing the atoms, and they are actually setting up a wave which it can travel through this material. This is one way of thinking. Okay, other way of thinking is like this. These phonons are nothing but units of vibrational energy that can arise from oscillating atoms within the crystal, that I have already told you. So as a solid consisting of specific repeating 3D basically arrangement atoms, so atom has behave as the connecting by springs, okay, where they bonded in a crystalline lattice. Now thermal energy makes this lattice vibrate. This can generate mechanical waves actually, which can be actually heat or sound. So packet of waves can travel through this crystal with a different energy and momentum. And quantum mechanics, these waves can be considered as particles. So phonons and photons, they can be correlated. Photons are actually quanta of energy, phonons are actually quanta of heat. They are similar, but quanta of vibrational mechanical energy is what is phonon is. Now we know that photons do not interact, but phonons can interact in a material. So hope this you have understand. Now to make it very clear, the crystalline structure is basically 3D, right? Like in case of BCC or FCC or hexagonal structure in a metal, the atoms are arranged in a nice manner. So if you put it on a plane, okay, that's how the FCC structure will like ABC, ABC, ABC stacking, like it will look like. So now they are arranged like along a line. You can assume that. So they are connected by springs, right? Or let me just show it separately. They are connected by springs. Okay. These are the atoms. So they are connected by spring. I am telling again so that you understand, don't forget. So now if you heat to the temperature, this atom, okay, let me just go there. What is that? Yeah. So this atom, so if you apply heat, this atom can move like this. So this similarly for this atom also will move like this. Because of this, a lattice wave will be traveling through the material, and that is what is known as a phonon. Correct. So that is exactly what is shown here. Now in terms of energetics concept, in terms of energy concept, in terms of potential energy concept, this can be explained also in the following manner. How we can explain that? Well, as you know, we know that if I have two atoms sitting side by side, their energetic balance depends on attractive force and repulsive force between them. Attractive force is basically attraction between electron cloud and the positive, that is the proton or the nucleus of the material. And repulsive force is basically electron cloud overlap. Okay. So the balance of these two forces will provide us the equilibrium positions of the atom and energy, and that is what is given by R0 and EV, right. So now as you heat it up, these atoms are trying to oscillate from the mean positions of R0. Okay, they will oscillate. That is obvious because you are providing energy. So if the atoms are providing energy, they will try to move, and then once they try to move, so they will go away from the mean equilibrium positions. Okay. So as they go away, this push pull will easily happen. So that is what is shown here. This is the equilibrium position, the deformed position. You can see in the deformed positions there is a motion of the atom at n minus 1 positions compared to n and n plus 1 positions. So one can actually set up equations based on this movement of the atoms actually easily, which we will see much later, okay, which we will see in the next couple of slides also. So as you know, this kind of concepts are easily available in many books. Most important books which you can follow is the solid state physics by KANPUR-NPTEL, and it is very nicely described there. And let me show the book. This is the book, Solid State Physics by KANPUR-NPTEL. You can see this is nicely, Charles Kittle's book nicely describes all the concepts very easily. So phonons are very important in condensed matter because they play very important role in thermal conductivity and electrical conductivity. Not only that, they also provide many other concepts. Okay. So now, as you see, I am showing you C positions of the atoms, which is one at n minus 1, one is n plus 1, and with the displacement of u n minus 1, un plus 1, okay, because of thermal energy, right. So n is the level of nth atom, okay, of the total n, and let us suppose distance between the two atoms is a, okay. Distance between two atoms is a, if we assume that, and mass is already given as m, right. So if you do that, a simple mass, simple balance calculation means simple displacement balance calculation. You can write down this equation 2c un plus c is the elastic constant. Why you are considering elastic constant? Because the springs actually. So whenever you are talking about the motion or the spring expanding or contracting, you always consider spring constant. A spring constant is what is known as elastic constant actually. So this is can be written like this. Okay. Why you are considering minus 2n? Because this central atom is basically pulled by both the two other side atoms, like which is as n minus 1 position, which is n plus 1 positions. This must be equal to mass, okay, m multiplied by acceleration, right. You should know that this is nothing but Newton's laws of motion. The force is equal to mass into acceleration. So force is this elastic constant c, this is elastic constant c multiplied by un is the displacement of the atom n, or at position x equal to xn, plus this is minus because this will be pulled, and then this c is un plus 1 and n minus. Okay. So now we can solve this equation very easily. All of you have done that. So solution is expected to be, this will be oscillative solutions, and this is normally done by discrete Fourier transformations, and so therefore un will be obtained like this. Okay, here n a k by twice pi going 1 to n q k exponential I k n a, right. You must be thinking what is k. K is the Fourier space constant. Okay. Normally it is inverse of the distance. Okay, that's all. It's like in case of photons, k is twice pi by lambda, right. So in this case also its k is twice pi by a is the interatomic distance, correct. So q is known as a normal coordinates continuum field modes. Okay. And you can always, if you make this equation and put it there, This is a solution of the equations. You can get two couple equations, and one of them will give you thermal acoustic modes, and another one will provide you the thermal modes. Okay. So that's how actually one can solve these linear problems of chains very easily. But in reality, they are not linear chains. They may be linear chains, but they will not be in one dimension, they will be in 3 dimensions. So therefore, one needs to consider the 3-dimensional structure of the material and do these calculations, which will be very complex. That is why normally we do not do it in the literature. And this is the phonon dispersion curve, you can see between this omega k, okay, that is what is your dispersion versus the k space. You can see k is going minus pi by a to plus pi by a, right. The k is basically always given as twice pi by a. A is the distance. In case of photons, we use twice pi by lambda. Lambda is the wavelength, right. So once you do such a kind of mathematical analysis in unit cell, exactly shown there, this is how the phonon dispersion curve will like. What does it mean? It means that the energy levels which are permitted, or the vibrations which are permitted, is given by these two curves. All of you remember that in case of metals, the energy band looks like this. The EK curve also looks like this. They looks like this, right? So that's a similarity between these two, but they are not similar always. Remember that. So because there will be some gaps here and there will be some small gaps. Oops, it goes like that. So it can be like this, which are not allowed, energy band and levels which are not allowed for the electrons. Okay, that's for the bulk actually. So this is something which is very important, and you should understand it. Okay, now one can do this statement quantum mechanically also by doing Hamiltonian concepts, which I am not doing it because you may not need it for your purpose. Fine, one can actually think of this chain consisting of two sets of atoms with different masses, M1, M2, and do the similar equation. I think that you should do as a part of assignments also and solve this problem. Okay, this is very, very important to do this kind of simple solution of the simple differential equations using certain conditions, boundary conditions and initial conditions. Okay, so therefore in a linear chain, this is exactly I showed you. This is how what will happen, a displacement pattern in a linear chain when you are talking about atomic vibrations. Atoms will move like that way from their mean positions to the both the sides actually, left or right, and that will lead to pull and push, what I discussed in the last lecture. Well, so this is the equations I told you, and this is a solution of the equations which has two parts, exponential part you see here, and this is the time dependent part. Okay, so there are two parts of the solutions, and as usual, and the two parts of the solution will give you the whole solution of the whole problem. This is not difficult. And now what I am asking you to do is that you have a two different mass of the sitting, not same mass. Then how to derive the equation and how to solve the equation, that is what is the assignment for you. Well, so in a nutshell, this is what is phonon, and these waves will lead to heat transport from material from one part to the other part. Now, what happens in nanoscale? Let us discuss. Okay. As you know, let's first talk about electrons, then we will go to phonons. In any materials, electrons will occupy bonding and antibonding orbitals. Let us start from there, correct? And so therefore, you can have electrons can be quantized, the energy levels, and they will be forming bands, and this band structure is well known in the materials. So they can be staying in the valence band, the conduction bands. The energy gap between the valence band and conduction band is known as the energy barrier or the band gap, right? So in a metal, there is overlap between the valence band and the conduction band. That means there is no band gap exists in a metal. So therefore, electrons can easily move from the valence band to the conduction band. That is why we say that in a metal, electrons are not bound to a specific atom, they are free. And we always call them as a free electron gas, because they behave like a gas. They are moving from one place to other place. If you put a gas here, and if you allow them, it will diffuse from one place, this place to some other, one corner of this room. Okay. Same thing in a metal, electrons are freely moving. So therefore, there is no band gap. But in a semiconductor or an insulator, there is a definite band gap. Electrons cannot simply freely move. So in a semiconductor, band gap is small, so that if you provide some energy, thermal energy, or maybe some dope with some elements, then you can actually move the electrons from valence band to electron bands. Insulators, you cannot do that, because the gap is so large, electrons can no longer travel from valence band to the conduction band. And this is what is the common notion of the electronic structure in a material, that we all know, correct? Everybody knows in this world that this band structure exists in a crystalline material, correct? So each band has a width that reflects the interaction between the atoms, and the band gap between the conduction and valence bands, which reflects the original separation of the bonding anti-bonding states. This is something which you should remember. So now what happens in a when you have nanoparticles, right? So let us compare bulk versus nanoparticles in comparison to density of states. In a bulk, like here in metal, because in metal you have free electrons, in a bulk you can see the conduction bands and the valence bands, they are overlapping, and this is the Fermi energy level to which the highest energy level to which electrons occupied, energy bands to which electrons are occupied. So there is a specific band, right? Electrons can remain there. But as you make in nanocrystalline states, there will be no specific bands. Electrons will stay even in different discrete energy levels. That is what is shown here and there. You can see discrete energy levels electrons can stay actually, right? Am I clear? So in 3D, the density of states will look like a continuous band. Okay, okay. This is the density of states versus energy plot. So you can clearly see for 3D materials, this will behave like this. As your energy level increases, the energy level increases, the density of state is increasing. Am I clear? So that's because you have large number of electrons and they're free to move any direction, that's why. But the moment you reduce the size of the systems and make it nanocrystalline, energy bands will undergo discretization. Like here, it's a 2D material, that is a thin film on a substrate. You can clearly see instead of a continuous band which is existing in the last case like this, okay, you have a discrete energy levels like that. Why does it happen? That's mainly because of the size. Okay. What is the effect of size? That's very simple. Electrons have specific wavelengths, right? So when the wavelengths of the electrons will be matching with the size of these thin films, okay, or size of the matter, then there will be interference coming from the size effect, right? That is what is known as the effect of dimensionality. Now, if you do a 1D, again there will be more further discretization will happen, and 0D it will be like a discrete levels. So this discretization of this continuous spectrum is what is known as the quantum confinement. You are saying, so there are two words there, quantum and confinement. So what I mean to say is that electron energies are confined to these levels. In between they cannot stay. They cannot occupy those energy levels. They are not allowed actually. And that's coming because of the low dimensionality of the system. So in a zero dimensional material where x, y, z directions are nanometric scales, electron energy is bounded. So electrons can only take up specific energy levels. It cannot move into other energy levels like these which are vacant positions. And this is known as a quantum confinement. It's just like electrons in a well. So if you put electrons in a well of length L, what will happen to the energy bands? That's exactly the same thing happens in a 3D. correct, or in 1D or even 2D. In a semiconductor, between a bulk and nanocrystals, again same thing can happen, but only there is a band gap, right, EG. Correct. Discretization can happen both in the valence band as well as in the conduction band. It can happen in both cases. Insulator, it doesn't matter, it doesn't make any sense, that's why we don't discuss much. So, quantum confinement is a very simple problem. It is similar to a famous particle in a box situation, and can be understood by simply examining the Heisenberg uncertainty principle. What does it tell us? It says that more precisely you know the position of a particle, more uncertainty you have in momentum, right. Therefore, more partially confined localized a particle becomes, broader will be the range of its moment of energy. So, the moment the directions or the size of these spatial dimension x, y, z are confined, they are smaller, fixed, okay, the broader will be range of its moment of energy. Okay, that is what is the situation. And this is manifest as an increase in the average energy of the electrons in the conduction band equal to increase of energy level spacing and the larger the band gap. So, band gap of spherical quantum dot is increased from its bulk or value 1 by r square, where r is the size or radius of the particle. Okay. So, now as you know, if I already discussed the particle in the box situation. What is the particle in the box situations? If you put a particle in a box, suppose in case of 0D, in case of 2D, let us start with that, and the 2D is here, okay, and L is the width of the box, well, the width of the box here, L, in 2D. In 2D, you have one of the dimensions is nanometric, other two dimensions are non-nanometric domain. So, you need to consider only one of the directions, that is x. So, the energy levels will be varying like this, mu square h cos square by 2 ml square n x square. Well, you may be thinking how this equation is derived. This equation is derived simply solving the Schrodinger equation, and by putting some kinds of basic conditions or the boundary conditions actually. But I do not want to solve these things, it is available in the books actually, you find that. So, now h cross is h by 2 pi, and h cross by m or 2m is basically momentum, okay, you know that, basically it is coming from the momentum, all of you should know that. And L square is basically coming from the length of the box. So, therefore, its energy E n, which is the energy of any of the band, it depends on n x square, correct, only in x directions. So, you can add up this for 1D and 2D. In 1D it will be nx square plus ny square, and 3D it will be nx square plus ny square plus z square. So, what does it mean? In 1D energy levels are quantized only and confined in the x directions. Y and z, they are free to move. There is no specific confinement of energy levels in the y and z. Electrons can take any energy levels they want in the y and z directions for 2D materials. For 1D, z directions are free, x and y are not free. For 0D, none are free. So, one of the dimensions of the nanostructure, that is one of the L, what is the separation between the energy levels? That is very clear. That is the effect of L. So, leading to spectrum and discrete energy levels. So, discrete energy levels which is shown you here, this is coming because of that solution of this problem. Okay, solution of these quantization problems from the quantum mechanics. And this whole thing is known as a quantum confinement or the aspect of quantum confinement. So, now as we discussed, electrons can get quantized, confined, or they can undergo quantum confinements. Phonons can also, because phonons also have valence. So, if the valence of the phonons it becomes same as the dimension of the material, then phonons can also be undergoing the similar kind of situation or confinement situations. Okay. So, what will the effect of these aspects, the confinement of electrons and confinement of the phonons, what will the effect of these, okay, both of these two, how, that is very important. Okay. So, how we are going to deal with it. So, let me just discuss a few cases today, one case maybe, and then we will come back to the next lecture. And this whole thing is nicely described in the book of by Michael Ashby and others. So, in the bulk homogeneous solid materials, wavelengths of the phonons and of the electrons will be much, much smaller than the length of the material, length of the microstructure rather. Let's talk about microstructure, because length of the material may be different, but the grain structure microstructure is what is very important. So in a homogeneous bulk material, the wavelengths of phonons or the electrons will not make any difference at all, because this length of the microstructure is much, much bigger than the wavelengths of this material. But in nanomaterial, length scale of microstructure, it will be of the similar scale as the wavelengths of the electrons or the phonons. Okay. So therefore, the quantum confinements is bound to occur or bound to take place. We will talk about phonons first. So in nanomaterial, quantum confinement comes in several ways, right? You have 0D, 1D, 2D nanomaterials. In 0D nanomaterials like nanoparticles, quantum confinements, as I discussed, can happen in all the 3 directions. In one-dimensional nanomaterials like nanowires or nanotubes, confinement happens in 2 directions, and 2D nanomaterial like a thin films or maybe nanocoatings, quantum confinement can happen in 1 direction. That is exactly as shown in this slide. So in 0D it can happen in 3 directions, in 1D it can happen in 2 directions, and 2D it can happen in 1 direction. And this quantum confinement effect is the same for the electrons also. So, a good way or a very good way to understand this quantum confinement is to consider that presence of surfaces in 1D, 2D and 3D materials, or 2D and 1D and 0D materials, not 3D. And these surfaces can cause change in the distribution of the phonon frequency, their interactions. So as I tell you that unlike photons, phonons can interact and they can change the velocity after the interaction. So one group of phonons can come and then meet with other group of phonon, and then the resulting phonon can have a completely different velocity or completely different frequency or wavelength actually. It's possible, which is not possible in case of photons. So therefore, both the phonon wavelengths and the appearance of the phonon modes can get changed. And these processes can lead to change in the velocity of the phonons. And that can lead to, that is noticed as a group velocity, as you know. And this is nothing but a group of ring of waves forming when you throw a stone in the water. If you throw a stone in the water, a ring of waves forms. And if you have several stones falling on the water, several ring of waves falls. And then they come and interact and create a new wave. And when they create a new wave, the group velocity of these waves will be completely different from the individual waves. So this is something which is a unique thing can happen in phonons. And this is very important, that this interaction of the phonons actually depends on the dimension of the material, right? Now, so therefore in 0-dimensional structure, what happens? In 0-dimensional structure, what can happen? The 1-dimensional, so a phonon bottleneck occurs in 0-dimensional nanostructure. It will be correct. Phonons cannot move very easily in any directions. That's what is called phonon bottlenecks, because all energy levels are quantized or they confined. So because of the confinement in x, y, z directions, phonons cannot move. So you can make a 0-dimensional nanomaterials like quantum dots completely insulated out of metals. Can you imagine that? Metals can never be insulated. Insulated in the sense of heat transport, right? But you can make it. You can make it by confining the electronic energy levels and the phonon energy levels in a 0-dimensional material. This is a real bottlenecks. So that's why many of these quantum dots can be used for insulators. Okay, what happens in 1-dimensional nanomaterials, which is very interesting. 1-dimensional nanomaterials has 2 dimensions in nanometric domain and 1 other dimensions in micrometer domains. Okay, so they can act as like a phonon waveguide, similar to like optical waveguides, optical ones for lights. Okay, so for example, if you take a carbon nanotubes, several investigation shows carbon nanotube has a very high thermal conductivity along the length of the tube. That means what? The phonons are actually moving very fast in the length of tube, just like waveguide. Okay, so and it has been found that this value of thermal conductivity can reach as high as 3000 watt per meter per Kelvin. Remember, for pure copper, which is very good thermal conductivity, the conductivity value is only 400 watt per meter Kelvin. So we are talking about orders of magnitude higher of thermal conductivity in common nanotubes in the direction of the tube. And that can mainly happen because of what? Because of basically this waveguide, because the phonons cannot move freely along other two directions which are spatially confined. Phonons move very fast in the z directions. Okay. So that's something which is very interesting. Now what will happen in 2D materials we will discuss in the next lecture, because the thin film other things will come into picture. So this is something which you should remember. So this what I discussed in the lecture, let me just summarize. So I talked about thermal transport. Thermal transport happens because of the electron and as well as the phonon in the materials. Electrons, we know that they can easily absorb energy and take the energy away. Phonons are something new. Phonons are lattice vibrations. They are created because of the motion of the atoms from the mean p positions, leading to push and pull of the atoms and creating a traveling wave in the material. And these waves can take the energy from one part of the crystal to the other part of the crystal. Interestingly, nanomaterials, both the electrons energy levels as well as the phononic energy levels can be confined depending on the type of nanomaterials, 0D, 1D or 2D. And this is a significant effect on the thermal transport. And I showed you the case of 0D and the 1D materials today. Thank you.